Hello, this is Joe Hartman with intraoperative and Sentient Medical. This is the fifth or sixth video in the series of the CNIM crash course. This one is going to be going over some of the electrical components. First, we're going to start off with the atom. The part of the atom that gives an element its identity is its nucleus. It is made up of two kinds of particles, the proton and neutron. Negatively charged electrons surround the nucleus. An ion is an atom that has lost or gained one or more electrons and now has a charge. So this is, back to middle school type science, but it's going to kind of build up a little bit, and so it's good to have some of this foundational stuff. A charge. If an atom has more or less electrons than neutrons, that atom acquires an electrical charge, which is measured in coulombs. There are two kinds of charges, positive and negative. Like charge repels, unlike charges attract. Positive charge comes from having more protons than electrons, and a negative charge comes from having more electrons than protons. Electric force between two charges depends on the charges and the distance between them. Substances can be classified in terms of the ease with which charge can move about their surfaces. Conductors are material that which charge can be moved about freely. That's kind of our metals that we use, especially on like the recording EEGs, stainless steel versus gold versus platinum. Insulators are material in which electric charge is not easily transported. So that's your plastics, or sometimes like signal gear has insulation around their electrodes to make sure that it isolates better the intramuscular recording that you're trying to get and not pick up any far field EMG activity from somewhere else. Resistors are material that prevents conduction and convert electrical energy into heat, measured in ohms. So your skin can be considered a resistor when you're stimulating an SSEP. It's preventing that conduction of electrical activity, and if your settings are inappropriately high, you can cause burns because it takes on the heat. Electrical charge can be measured using the law for the forces between charges, or Coulomb's law. We'll look at that a little bit more. Coulombs and amperes. Coulomb's law gives the force of attraction or repulsion between 2-point charges. The coulomb is actually defined in terms of electric current, the flow of electrons. In a household electric circuit, a 100-watt light bulb draws a current of about 6 quintillion, or 6 followed by 18 zeros, charge carries per second. It's ridiculous to speak of current in terms of charge carriers per second, so it's usually measured in coulombs per second instead. So a coulomb is equal to approximately this huge number of electrons. A current of 1 coulomb per second is called an ampere, and it is the standard unit of electric current. A 100-watt bulb in your desk lamp draws about 1 ampere of current. So that's the typical example they give looking for 1 ampere. Same charges repel, opposites attract, and then the current flow is opposite, and that's measured in coulombs per second. Electromotive forces. This is kind of an older term, but we should probably know it for the CNIM. It refers to the voltage generated by a battery or by the magnetic force according to Faraday's law, which states that the time-varying magnetic field induces an electric current. So anytime you see someone's law, please remember what the definition of it is, and if there's any accompanying equation, have some familiarity with that to be able to work it back and forth. The electromotive force is not a force, as force is measured in newtons, but a potential or energy per unit charge measured in volts. So there's a couple of terms in that sentence there that you should know. One is a potential, and its definition of energy per unit charge, and it's measured in volts. Voltage represents the pressure or driving force that impels the charge carrier to move. In general, for a given number of charge carriers, higher voltages will produce a faster flow and therefore a larger current. Resistance is the measure of the opposition that a that a circuit offers to a flow of electric current. You might compare it to the diameter of a hose. So we see the picture on the left. Open hose, less resistance, the water flows through. More resistance, pinch the hose, less water flows. When 1 volt is placed across a 1 ohm of resistance, assuming that the power supply can deliver an unlimited number of charge carriers, there will be a current of 1 ampere. If the resistance is doubled, the current is cut in half. If the resistance is cut in half, the current doubles. Therefore, the current flow for a constant voltage is inversely proportionate to the resistance. Electric circuits always have some resistance. There's no such thing as a perfect conductor. So this is all kind of leading up into one of the big laws that you have to know, which is Ohm's law. An electromotive force of 1 volt across a resistance of 1 ohm will cause a current of 1 ampere to flow. That's a sentence that you should know going into the test. This is the classic relationship in electricity and is stated generally as Ohm's law. If the electromotive force is doubled, the current is doubled. If resistance is doubled, the current is cut in half. Over on the right here, we have a picture showing Ohm's law where V is the voltage. That's the same thing as electromotive force that we've been talking about earlier. I is the current in amperes, and R is resistance in ohms. And you'll see in the bottom that you can switch this equation around. So more than likely, they're going to give you 2 variables, and they're going to ask you to figure out the third. So if you just memorize one equation, I always remember VIR, velocity equals, or I'm sorry, voltage equals current times resistance, and then you can just plug and play with your calculator and figure out whatever it is they're looking for. Tools for measurement. An ohmometer is an electric instrument that measures electrical resistance, the opposition to an electric current. That's what we're kind of used to, at least in the operating room. An ammeter is a measuring instrument used to measure the electric current in a circuit, the leakage current. A voltmeter is an instrument used for measuring electric potential difference between 2 points in electric circuit. So things that would be useful if you're looking for Ohm's law. Direct current versus alternating current. Constant electromotive force causing electrons to move in a single direction. The result is a direct current, where opposition equals resistance. If we're talking about current flows momentarily in one direction, reverses itself, and then flows in the opposite direction, that is alternating current, where opposition equals impedance. Current reversal is periodic and typically occurs at 60 times per second, resulting in a familiar 60 Hz cycle artifact seen in many neurophysiological recordings. So this 60 Hz is an alternating current. The electrical current used in the OR from power lines is an AC. Alternating current is more harmful to the human body than direct current. 3 amperes of direct current could pass through the human body without any harmful effect, whereas only 100 milliamps of alternating current can cause ventricular fibrillations. And I think we'll look a little bit more into the risk of shock and ventricular fibrillations a little bit later. So monitoring in an electrically hostile environment. Since we're recording electric activity, you think we might have some problems with our recordings. So we're going to try to talk about how we battle every day to get rid of some of this electrical noise from the operating room. Electric displacement currents. Background electric current or electric fields are produced at 60 Hz noise in a bioelectric recording. This can occur by 2 similar mechanisms. In the first, the background electric field couples to the electrode leads. In the second, the background electric field couples to the conductive volume of the subject. In either case, it is a 60 Hz potential relative to the ground, which causes additional current to flow to ground. While the resulting current may be similar in each of these 3 leads, various impedance imbalances produces 60 Hz noise in the difference of the 2 leads. We assume that most electric displacement coupling occurs through the electrode leads. So that is why it is very important for us to get good impedances on our electrodes and very similar impedances from one electrode to the next. Things in the OR that can cause this 60 hertz or 50 hertz in the UK, things that we're all familiar seeing, the drills, the fluid warmer, the C-arm, the anesthesia machine, bear hugger, drills, navigation, scope, the bed itself. So anything that has a power cord or a power supply or a motor in it or magnets within it is going to have some additional noise to our recordings. Most artifacts like muscle activity, EKG, room wiring, and electrical devices are in millivolt ranges while we are dealing with microvolt potentials. So the size of the noise is much larger than the potentials we're recording. If we look at some of the average sizes, which you should probably be pretty familiar with, our bears is 0.1 to 0.5 microvolts, SSEP 0.5 to 3, VEPs 2 to 10, EEGs 10 to 50, and a triggered response gets up there into the millivolts. Where their stuff, a wall socket is around 120 volts. So again, it's not even a fair battle. EEG artifacts, something from the human's physiological process, is EMG, eye movement, EKG or ECG, and respiration. Non-physiological ones is the 60 hertz interference, EEG electrodes themselves, and other environmental sources. Ways that we can fight the noise. Sometimes these things are already built into our equipment. Other things are things that we can manipulate ourselves. So the electrode metals and insulation, either being on the production side of things or the selection side from us to what company we use and what kind of metals we use. Doing everything to lower impedance, like scrubbing the skin off the head, making sure our needles are buried deep within the skin. Using short, twisted wires grouped together. So the long ones are more likely to get bunched up, or you kind of loop them in circles. Whenever you loop a wire, it picks up noise much easier. The twisted wires, we'll see in a little bit, but those are much better at seeing extraneous sources as similar, so our equipment can just get rid of it. And same thing when we group it together. So whenever we have wires, we want them as closely wound together as possible. We can create distance from noise. We're used to doing that, especially people that use their head box on the table. Sometimes that doesn't work out and they got to put it back towards them a little bit or place it on the ground or whatever to get away from that noise source. Create distance from the stimulating and recording electrodes. Avoid extension cords. You should be plugging right into the wall, and you should be plugging into one that has the red face to it. That's the one that's the hospital grade. You should have the patient properly grounded as well as your equipment. High and low filters set appropriately. Averaging, this is if we're evoking a response, the more averages or sampling, we can get rid of the waveforms that we don't want within our traces. Smoothing is good up until a point, and then you can actually start losing data that you want to collect. Rep rates, again, you can we went over that as far as where you set them and the ranges that you can use them in. The differential amplifier and common mode rejection, we'll get into a little bit more later on, but this is what, when we use two electrodes to see similar or different potentials and what that does as far as reducing or including other samples of artifact or other physiological responses. Amplification, again, that happens in our equipment without us really having any effect on it. Analog to digital filters, same thing, and notch filters, same thing. Electrodes. The recording electrode montage should consist of one type of electrode with no mismatching of metals. Reusable electrodes with inconsistent surfaces can create uneven current densities, so check the integrity of the electrode. Applied with sufficient conductive gel to ensure low impedances. That's if you're using the gold cups or something like that. Abrading the skin or using subdermal needles eliminates galvanic skin response or the electrical conductance of the skin, which varies with its moisture level. Adhere surface electrodes should result in a secure placement. If you're using those EEG leads on the cup leads, then most people are using collodion soap gauze, and you blow on it with the cold air, and it sticks pretty well to the head, and then you squirt that conducting gel in there just to make sure that you have a good a low impedance and a good contact. Separating the electrode leads and cables will reduce the chance of electrical coupling between adjacent lines. Okay, so here is a simple picture. We're looking at the resistance from the skin and how our equipment utilizes that to come up with an impedance read, and where we need to make sure we have a correct level of impedance. So the impedance level we need to make sure is less than 5,000 ohms or 5 kilo ohms, and inter-electrode difference should not exceed 2,000 ohms. So you need to know those two numbers for the exam. All electrode impedances must be low. Whenever electric current flows through an impedance, there is an associated potential drop. All electrical impedances must be identical, or as close as possible. It's never going to be identical. Differential amplifiers filter out potentials that are common between two inputs. So that's that common mode rejection. Anything that's common to both inputs is rejected out. Short and twisted electrodes. The shorter the electrode, the less antenna to pick up ambient noises. The shorter the electrode, the less looping you have to do if there's slack in those electrodes. And twisted electrodes with similar noises will have or similar noise output will be better affected on the common mode rejection rate. And we can see the difference between electrode wires that run in parallel versus those that are twisted, the difference of +8 versus 0. And the picture below that, we see source 1, the positive, has that upgoing wave. Source 2, or the inverting, the negative side, has that downgoing wave. And the output is, after the negative is inverted, it's additive to the non-inverting positive, and we have that large amplitude. Versus the noise, where it is exactly the same because it's picked up from, say, the lights above. The halogenated lights are giving off noise. Those electrodes that are at a distance far enough away that it sees that noise source is very similar. So when it goes to that negative or the inverting portion, it will subtract it out, and we have a isoelectric. Parasitic capacitive coupling. Capacitive coupling is often unintended, such as the capacitance between two wires next to each other. Often one signal can capacitive couple with another and cause what appears to be noise. To reduce coupling, wires are often separated as much as possible. You're stimulating electrodes in your Bovie wires from recording electrodes, magnets, motors, power supplies, and other cords. AC devices in the recording environment introduces 60 hertz noise into the data. This occurs because electric and magnetic fields incident over the electrodes leads a body generator potential, which adds linearly to the signal. So it's just saying that all of these different equipment in the room, and even our electrodes, has this magnetic field that can be produced off of it. Our electrodes are pretty good because it has that nice insulation around it that it can not give off or take in as much of this magnetic field, but it's an imperfect system. The ground, the common electrical connection for the electric circuitry of the recording equipment. All voltages and impedances are measured with references to it, usually placed between the stimulation site and the first recording electrode, but as long as there's the electrode to patient connections are adequate, or you have low enough impedance, the location of the ground electrode does not really matter that much. A typical location for the ground is the patient's shoulder. The differential amplifier cancels the potential of the ground electrode out, similar in both inputs. With a poor ground electrode connection, the differential amplifier input effectively becomes the ground electrode potential. 60 hertz artifact and poor localization of the cerebral electric activity can result by the unexpected introduction of the signal coming from an EEG ground electrode into one of the or more channels. The IOM equipment. All recording electrodes are attached to the amplifier through a head box. This protects the recording system against interference during the use of electrocautery by limiting the amount of current flow from the patient to the amplifier. It can also serve as a selector for switching among different electrode groups depending on the need of different phases of an operation. Biological signals, very small, noise, very big. The input of the amplifier has components of many different signals. The biological signal that we aim to measure, or our evoked potentials. The biological signal that we do not want to measure, like cortical, cardiac, muscular, and other biological activities. 60 Hz interference signals and its harmonics. Interference signals arising from the electrode tissue contact. Environmental interferences like the electromagnetic, electrostatic, radio frequency interferences, and noise of the amplifier itself. So what we observe can be divided into two different areas. What we see is a complex waveform that is made up of the signal that we're trying to get and the noise that is overriding it. And that is exactly what our equipment is trying to separate out. The differential amplifier. Noise will be picked up in active and reference electrodes and are very repetitive, and it's easy to identify and eliminate. The basic differential amplifier measures the voltage difference between two signals at each input. Ideally, a differential amplifier should amplify only the difference between the signals present at the two inputs and reject all signals common to both inputs. So not only do we have a signal that comes in and rejects the like activity, which is most likely noise, our amplifier will also increase the amount of size of our non-common inputs. And so we see there A, B, C, and D, and we're looking at how the differential amplifier gets rid of the common noise and amplifies our potentials. Common mode rejection. When the same voltage is applied to both inputs, the amplifier output is 0. This is due to reverse polarity, or positive-negative sign, of inverting electrode input's voltage and adds to its non-inverting electrode input. This is in effect a subtraction process. 60 cycle hertz. Noise will affect equally both inputs of a differential amplifier and have a 0 total effect on the output. The output of a differential amplifier theoretically is noise-free and represents only neurophysiological activity. Common mode rejection rates, some math along with it. The ratio of the differential gain over the common mode gain, for example, the CMRR equals the differential gain over the common mode gain. Sometimes on the CNIM they will ask you to plug in and find a missing component of that, or they'll straight up ask you what is the equation used for the common mode rejection rate, and then you have to know it's differential gain over the common mode gain. Typically, the CMRR values for a good EEG amplifier is 10,000 to 1. Again, that's just another number that you have to have memorized and associated with the CMRR. Input impedance of 10 megaohms to avoid signal attenuation and degrades the active reference difference. If there is a common signal in both inputs 1 and 2, then only 1 out of 10,000 units will be amplified. This ratio can be stated by a decibel by finding the logarithm in the base of 10 times 20. An easier way is to count the zeros in the ratio times 20. Another way to saying it is if the ratio is 1,000 to 1, has a 60 decibel CMRR, 120 decibel will have a ratio of 1 million to 1, since 120 divided by 20 is 6, and there are 6 zeros in 1 million. Amplifier gain. The ratio of the voltage of the signal at the output of the amplifier after amplification to the voltage delivered to the input. So gain equals voltage out divided by voltage in. 10 to 10,000 are common numbers. Display sensitivity in the waveform expressed as unit of voltage per division. Small differential signals applied to the inputs is called the differential gain. This is the gain given to the voltage that appears between two inputs. Large signals applied equally to both inputs is called the common mode gain. This is the gain given to the voltage that appears on both input terminals with respect to the ground. Ideally, similar voltages in both channels will be rejected and they result in a common mode voltage gain close to zero. An amplifier is a crucial component due to the size of the recording response. Remember, we have that little tiny bare, so as little as 1/2 of 1/1,000,000th of a volt for bare. So if input 1 is 20 microvolts and input 2 is 10 microvolts and the output voltage is 1 millivolt, what's the gain? So here we have a little bit of math. We have input 1 of 20 minus input 2 of 20 equals 10 microvolts. Gain equals volts out divided by volts in, or 1 millivolt divided by 10 microvolts, or 1,000 microvolts divided by 10 microvolts equals 100. So we actually had to know two equations there to come up with that answer. If the vertical gain is set to 200 millivolts per division, and the event you're recording is 3 boxes high, how big is the signal if the amplifier gain is set to 10,000? Again, not a very nice question, probably harder than anything you'll see on the CNIM. 3 boxes equals 600 millivolts. 600 millivolts divided by that 10,000 equals 60 microvolts. Analog versus digital filtering. Analog signals are precise, continuous, and smooth. It's the old pen and paper machine. Now it's hardware, resistors, and capacitors coupled together before the AD conversion. Digital signals represent discrete points in time, and their values are quantified to a fixed resolution rather than continuous. They are discontinuous, which is its weakness point. Digital can store and save data, edit demontage, edit sensitivity and time base, edit channels, and that's all of its strengths. The computer operates on binary numbers that are set in bits. A bit contains the smallest possible chunk of information, a signal on or off signal. The accuracy or resolution of Q of binary numbers is determined by the number of bits they contain. So here we look at the binary code on the very front, top right there, made up of 8 bits. 8 bits equals 1 byte. AD converter, the digital rate. So the AD converter converts the analog signal measured in volts per millisecond to a digital signal. Using computer software, the AD converter is given instructions to sample the incoming signal at a specific rate, read the voltage, and convert the voltage to a number. For example, the AD converter might be instructed to collect 600 points at 20 kilohertz. A digitization rate of 20,000 hertz is 20 points per millisecond, or 1 point every 50 microseconds. With these instructions, the AD converter would collect a digitized 30 milliseconds of the incoming signal, or 600 points times 50 microseconds, which equals 30,000 microseconds, or 30 milliseconds. So here is just picking up the sampling points. AD converter, it is critical that the digitized rate be set appropriately. If the rate is too slow, there will not be enough points to properly characterize the waveform. If the digitization rate is set too high, the waveform will be properly characterized, but the computer memory will be wasted. Collecting 150,000 points per second can use a lot of memory in a short time. So here we have pictures saying not enough sampled points, and one that's a proper amount of sample points. You can see when we don't have enough sample points, we lose part of the information that we're actually trying to assess. Horizontal or time resolution. So the epoch or analysis period or sweep length is determined on the timing of the potential. So VEPs comes around 200 to 250 milliseconds. Lower extremities, you have 100 milliseconds. ABRs, 10 to 15 milliseconds. and that's your analysis time, your epoch. The epoch is made longer than the interstimulus interval, so more than one cycle can be recorded, usually way more. The length of the analysis period is related to the number of points available for averaging. The dwell time, or bin width, is the reciprocal of the sampling rate, or the rep rate. So analysis time or analysis period equals the number of points times dwell time. Analysis period also equals the number of points divided by sampling rate. Most averagers offer 1,024 points per channel, 512 or 256 if multiple channels are used. So you do have to know this equation for analysis period in both forms and be able to figure out the analysis period. Bin width of 20 microseconds per data points or less is recommended. Again, that's just a number that you have to have memorized. Translation from the analog to digital is known as sampling or digitizing, and in most applications it is set to occur at regular intervals. The reciprocal of the sampling interval is known as the sampling rate and is expressed in hertz or samples per second. It depends on the number of addresses available per channel and the time for analysis, or the sweep time. The computer stores the voltage value at each address or bit or digital time interval, which is called the intersample interval, or dwell time or bit time. Those are 3 AKAs. The faster the sampling rate, or the greater the number of addresses per channel, the shorter the intersample interval, thereby gaining higher resolution. So in the example above, the example of sampling rate or dwell time in relationship with analysis time, with 240 millisecond analysis time, 50 Hz sampling rate is equivalent to 20 milliseconds of dwell time. So you just have to figure out that there's 12 intervals with a total time of 240 milliseconds, and that space in between each waveform there is 20 milliseconds. The analysis period must include the important peaks monitored. The sample rate or dwell time must be sufficient to resolve the highest frequency. At least 2 points are needed to depict a sine wave digitally, so the averager must be twice as fast as the fastest frequency, and that's the Nyquist frequency. That is another term that is commonly found on the CNIM exam. Usually 10 to 20 points, not the minimum of 2, are used for one cycle. So the Nyquist frequency is at least 2 points or twice as fast than the faster frequency. So if you're looking at delta waves and the fastest frequency is 4, then your averager needs to be twice as fast as that, or at least 8 points. Nyquist theorem: the sampling frequency should be at least twice as fast as the highest frequency contained in the signal. If we're looking at EEG, we know that the beta had the fastest waves that we are concerned about in the operating room, at least. These waves have a frequency that goes up to 35 Hz, so the high frequency filter would need to be at least twice that, or 70. In addition, other signals present on the scalp would include power line interference at 60 Hz and the EMG, which if present may extend above 100 Hz. So that filter will do well to get rid of those faster frequencies. To prevent aliasing distortion in the EEG from other signals, many digital EEG systems sample at a rate above 250 Hz, a digital sample for every 4 milliseconds. So if we sample this wave at 2 Hz, as dictated by the Nyquist theorem, this is sufficient to capture each peak through its signal at 1 Hz. If we sample at a frequency higher than this, for example 3 Hz, then there are more than enough samples to capture the variations in the signal. If, however, we sample at a frequency lower than 2 Hz, for example 1.5 Hz, then there's now not enough samples to capture all the peaks and all the troughs in the signal, which we see in the very last picture. The Nyquist theorem: examples of minimum sampling rate to resolve 50 Hz activity. If the available sampling rate is 20 milliseconds, this would result in a flat tracing by connecting the available dots. In order to reproduce the 50 Hz activity, shortening of the sampling rate or dwell time is necessary by adding more points with more intervals. This is equivalent to a 100 Hz resolution, or one that is double the frequency of the original waveform. So in A, we don't have enough sampling points, so we have a flat line, whereas in B, we have double that, so now we are able to pick up dots on both the upper and lower at the very minimum, and we have at least some wave that we can collect off of. So double it is the very minimum that we can do to collect some kind of wave to collect data. Aliasing. When a sample is performed too infrequently, the fast sine waves of the epoch will not be identified correctly. It doesn't have a minimum of at least 2 points within a single sinusoidal wave. If the sampling is not fast enough to place at least 2 sample points within the signal cycle, the sample will appear to be slower or longer cycle time than the original. Conservative designs actually calls for a sampling at a rate 4 to 10 times higher than the highest expected signal, and to also use a low-pass filter prior to sampling to eliminate signals that have frequency components that are higher than expected. Aliasing is avoided by proper filtering. So we have on the top one the appropriately adequate sampling signal, and the lower is aliasing signal due to undersampling, where instead of this faster frequency, we end up with this very slow-looking frequency, which is not what we're actually looking at. More examples of aliasing due to insufficient sampling rates: using available digitized sampling points of 20 per second or 20 Hz sampling rate, or 50 millisecond dwell time. 2, 4, 6, 10, 12, and 16 Hz sine waves are reproduced. The activity less than 10 Hz or half of the sampling rate can be faithfully reproduced, though the waveform are more distorted with higher frequency activity. The 10 Hz activity become flat, and the activities faster than 10 Hz can no longer be reproduced, becoming a slower frequency than the original signal. Signal resolution with various digitimer sampling rates. Signal resolution with the various signal sampling rates: the greater the number of samples available, the greater the resolution. Note small notched waves visible in 200 samples, shown by the arrows, per second were lost in the 50 samples per second. Horizontal resolution, generally 2 to the 9th power, or 512, or 2 to the 12th power, or 4096. Addresses should be available for each channel. Dwell time equals sweep time divided by the number of intervals. So if we have a 500 millisecond with 9 intervals, that equals to 55.55 millisecond sampling rate. The dwell time can also be expressed as a frequency. So our frequency of 1000 milliseconds divided by 55 milliseconds gives us 18 Hertz. The Nyquist says you would need 18 Hertz times 2 equals 36 Hertz as a minimum to prevent aliasing. The ACNS guidelines has at least 3 times the frequency of the original sampling. So that's just kind of working through this guy's question, which I probably should have read first, which says, what's the dwell time if the sweep time is 500 milliseconds with available addresses of 10 digitized points or 9 intervals? So if we go all the way back to the picture here, where we're looking at the different number of addresses, different number of intervals, the dwell time, and the total analysis time, we can now see this in mathematical questioning and how we need to be able to work through it. What's the dwell time if the sweep time is 500 milliseconds with available addresses of 10 digitized points or 9 intervals? What would it be expressed in its frequency, and how fast should it be? So I had that backwards. I should have had the question before the answer. The dwell time equals the sweep time, and this is pretty much the same thing as we just went over. Vertical resolution. Vertical resolution defines the amplitude. You want it to match the amplitude of your input to maximize the signal. The range of the AD converter is the largest signal that the converter can convert measured in volts. The resolution is related to how small a change the AD converter will detect. It's the precision of the amplifier or how finely the range can be divided. This precision is measured in the number of bits needed. Remember, 8 bits is the minimum needed for neuromonitoring. An n-bit ADC has the resolution of 1 part in 2n. For example, a 12-bit ADC has a resolution of 1 part in 4096, where 2 to the 12th power is 4096. So a 12-bit ADC with the maximum input of 10 volts can resolve in measurement into 10 volts divided by those number of points equals 0.00244, or volts equals 2.44 millivolts. The resolution is usually specified with respect to the full range reading of the ADC, not with respect to the measure value of any particular instant. In addition to setting the digitized rate of the AD converter, the digitization range must also be set. There are 4 possible range settings: negative 10 volts to 10 volts, minus 5 to 5, minus 2.5 to 2.5, and minus 1.25 to 1.25. The AD converter will assign each voltage a whole number between 0 and 4095, or 12 bits. Because there are only 4096 numbers to work with, the resolution will be different for each setting. So in the first range, we see range equals 20 volts or 20,000 millivolts, resolution of 4.88. Range 2 has 10 volts or 10,000 millivolts, resolution of 2.44. Range 5 has 5 volts or 5,000 millivolts, resolution of 1.22. And range 4 has 2.5 volts or 2,500 millivolts, resolution of 0.61 millivolts. Vertical resolution at the minimum of 8 bits. An 8-bit binary number can represent 2 to the 8th power, or one of 256 possible states at any given time. A 16-bit number, or 2 to the 16th power, or 65,536 possible states. If one were using an 8-bit number to represent an analog signal, the binary number would have at best a resolution of approximately 0.4%, or 1 over those 256 states over its range of measurement. Commercial EEG monitoring systems use 12 to 16-bit resolution. Remember those numbers, 12 to 16-bit resolution. More bits also create a wider dynamic range with the possibility of recovery from more artifacts. However, more bits increases the expenses dramatically on the system itself. So averagers with no bits have higher resolution, averages with more bits have a higher resolution, as we see 1-bit, 2-bit, 4-bit, 16-bit. Any gamers out there should be familiar with this. Nintendo, I think it was originally an 8-bit, but now we are up in like 64 or something like that, where the resolution or the quality of the image is way, way better. Vertical resolution limitations. An 8-bit converter, the range is divided into 2 to the 8th power, or 256 levels or states. If the AD converter had a range of 20 volts, the 20 volt range divided by the 256 levels equals 0.0781 volts, or 78,100 microvolts, which is way too large for neuromonitoring. That would be converted as a straight line. What if you wanted to see changes as small as 0.1 microvolts? If you add an amplifier with a gain of 781,000 microvolts, now divided by 0.1 microvolts, that takes care of the resolution. But what about the range? 0.1 microvolt steps times 256 levels equals 25.6 microvolts total. That's plus or minus 12.8 microvolts. Anything greater can't be resolved with an 8-bit converter. And so that's the reason why we don't use the 8-bit converter. We use higher, the 12 to 16. Vertical resolution limitations. If you're looking at a unit, your signal will be in the microvolt range, and you will probably want to amplify 5,000 to 20,000 times. For field potentials, your signals will be in the millivolt range, and you'll probably want to amplify 50 to 200 times. Instead of amplifying at the numbers of bits, what happens if you increase the number of bits on the AD converter? The max amplitude of EEG is about 50 microvolts, so it works out. So if you move to a 16-bit converter, that's 2 to the 16th or 65,000 levels. So a 20 volt divided by 65,000 levels is that small number, or 305.1 microvolts. At this new volts per level, you would still need to amplify, and the gain would be 3051 or 305.1 microvolts divided by 0.1 microvolts. Since we amplified, the gain affects the range, with 65,000 levels and 0.1 microvolts needed to see small changes. 6,553 microvolts, or plus or minus 3,276 microvolts, is the range. So with a 16-bit AD converter and a gain of 3,051, we can digitize the signal to the closest 0.1 microvolt and can handle an amplitude of up to 3,276. So it works. Vertical resolution limitations. A resolution of 12 bits or 12 or more bits is preferred, since the recording should be able to resolve EEG down to 0.5 microvolts and record potentials up to plus or minus several millivolts without clipping. For example, with a 0.5 microvolt resolution and a 12-bit analog to digital conversion, the maximum allowed excursion would be plus or minus 1.02 millivolts. This is the dynamic range of the system. Quantization errors. The quantization and encoding process cannot be infinitely accurate and can only provide an approximation of the real values present in the ADC's analog input. The higher the resolution of the quantizer, the closer the approximation will be to the actual value of the signal. Errors occur when a digital sample does not exactly match the analog signal strength it is supposed to represent. In other words, the digital sample is slightly higher or lower than the analog signal. Quantization errors are also called rounding errors because imprecise numbers represent the original analog. The quantization range of the ADC circuit depends on the high-cut filter frequency in the filter circuit and should be at least twice the value of this frequency. The following table summarizes the characteristics you could expect from ADCs that have theoretically perfect performances, which never really happens. The table also shows maximum sampling rate that is currently being supported by the best devices in each category. So these are some of the similar numbers that we went over. Remember, the resolution in bits is what we're mostly talking about as numbers to memorize. Don't mess around too much with the range, but you should be familiar with 12 and 16 going straight across. Those numbers might pop up. An isolation box, an additional isolation device typically internal to the amplifier box, is used for patient protection against electrical shock in case of equipment malfunction. The analog EEG system is found in these areas here, the low frequency, high frequency, and notch filters. The filters, which we went into much greater in a previous video, some artifacts at EMG characteristically have most of the energy in a frequency range different from that being collected, say, from an EEG. The amplifier can bandpass filter the signals passing the EG and attenuating the non-overlapping EMG. Conventional machines use analog filters made of resistors and capacitors. Analog filters alter not only the amplitude but also the relative timing of the individual wave in a signal. Modern equipment, on the other hand, relies on digital filters or computer programs that have a similar characteristic with analog filters as far as the amplitude attenuation is concerned, but they eliminate phase shifts. So I said before in that video, when you're messing around with the filters, we're looking at the phase lag and phase lead. If you're changing the analog filters, if you're using it, making changes to the digital filters, you will see changes into your amplitude, but not into the onset latencies. A resistor is a passive two-terminal electrical component that implements electrical resistance as a circuit element. So we saw that with the hose. You pinch the hose, that's the resistor, is the pinching of the hose. A capacitor is a device for storing electrical charge. Filters again, capacitors in series, resistors in parallel. Low frequency filters affect mainly slow waves and make them appear earlier than fast ones. RC circuits have RC circuits with the capacitor in series and the resistors in parallel. The output is attenuated at low frequencies but is nearly equal to the input of high frequencies. For our high frequency cutoffs, resistors in series, capacitors in parallel, they do ask that question. For high frequency filters, has the following resistors in series, capacitors in parallel, or does it have capacitors in series and resistors in parallel? You have to know which one matches up with which. High frequency filters attenuate fast components and makes them appear later than slow ones. The RC circuit with the resistor in series and the capacitor in parallel, the output is attenuated at high frequencies but is nearly equal to the input at low frequencies. Okay, that was a lot, and that's probably the heaviest section and the one that most people get wrong on the CNIM. My advice would be to go back, watch the video again, pause on each screen that has a lot of information. Don't get too bogged down with a lot of that advanced math, but if it's a simple equation, make sure you know the equation. If it's got the word law behind it, make sure you know that. Know the difference between capacitors, resistors, and all that, and when it comes into play, and how it affects with our filters. And that one just takes some time and understanding unless you have some kind of background that deals with some of that. So some of the PhDs in neuroscience or somebody that has electrical engineering background or something like that might be able to breeze right through that system. But I think the majority of us, that's new stuff and a little bit out of our comfort range. Also, I have some other posts that is good for the CNIM prep. I just wanted to remind you to look on the website also. So, this was just a single post on understanding far field potentials. And I have a couple of different ones on there that are geared towards the people taking the CNIM. Okay, that is it for this video, and we'll see you on the next one.